Hi everyone. This is actually the perfect talk to follow on Jean-François's work on elliptical yield curve. I'm going to continue on non-elliptical yield curves. So this is a work that I started at AVI and Uni Bremen, but now I'm continuing with Bruno Tremblay in McGill. I added some things since I registered my abstract with some work with Jean-François, with Niels Suter, and Louisa von Albedul. So first, maybe you already seen pictures like this. This is a Sentinel-1 image in the East Siberian Sea. And for me, it's beautiful. I always smile when I see this because it's full of these LKFs, and we see beautiful fracture angles. And like Jean-François explained, this is important because LKFs are the hotspot of processes in sea ice. So we have open water and thin ice formations. We have a lot of ocean air heat exchange. We have shear and convergence. So we have thick ice formation. So it controls the thermodynamics and the future dynamics, the future deformations of sea ice. It's a barrier for movement on the ice, and it's a path for navigation in the water. So it influences human and animal activity as well. So an accurate representation of the LKFs is really essential for accurate sea ice prediction. Now, when we look at this, we can wonder, as Jean-François said, what are the angles between these LKFs? And using deformation datasets, such as RGPS or other ones that are more recent, we can actually see if the angles that we see here are more acute or more obtuse compared to the direction of deformation. And we can look at the PDF of these angles. And so that's what we did with Niels and Louisa. And this is the distribution of the intersection angles between in RGPS dataset and in the Sentinel-1 dataset that's taken along the mosaic track. And we can see that we have a lot of small angles between 30 degrees and 60 degrees. I think the number is something like more than 60% of the angles are below 90 degrees. And it's, as also Jean-François talked about, in Cyrex, we see that models don't reproduce this small predominance of small angles. Now I will go to the sea ice rheology part. So rheology in models is arising because there is a lot of small-scale dynamical process in the ice. So interaction between flows. So we need this sea ice rheological model because the sea ice, depending on the direction of the stress and the amount of normal to shear stress, will react differently. You can see here a lead with a lot of small flows and how they will interact, and that's what we want to model. So for this, we use a yield curve and a flow rule. So we use the yield curve to model the ratio at fracture for different shear and normal stress. And we use, because it's a plastic model, there's a plastic flow rule, and the flow rule is the direction of deformation. You can see the angles, the little arrows on the yield curve. So that determines for each stress state if we're going to deform in convergence, shear, divergence, a composition of the three. And in previous papers, we showed that intersection angles are linked to the shape of the yield curve. There's two different theories, the Coulomb angle that is linked to the yield curve and the Roscoe angle that's linked to the flow rule. And I will come back to this. But then using this previous results, we can use the PDF of angles that I presented before and try to reconstruct a yield curve from this. This is a bit complicated, so we need to take some hypotheses. For example, that we use now a normal flow rule, a flow rule that's normal to the yield curve. And using this PDF, we can reproduce, we can create this kind of yield curve shape and compare it to shape that have been used in sea ice modeling, and it looks a lot more like a Mohr-Coulomb shape or a teardrop shape. So not like an ellipse shape. Looking at literature of sea ice models, we can see different yield curve shape have been used. So there is a teardrop and parabolic lens shape that were used in 2005 that use a normal flow rule, and there is a Mohr-Coulomb yield curve created in 91, which use a shear-only non-normal flow rule. You can see it only, the ice in this rheology only deforms in shear. So we're going to test these rheologies in a very simple experiment like I did before. So you take a rectangle piece of ice and you force it against a wall, and you see how is it going to deform with which angles, and if it's going to open or ridge. So we do this with the teardrop yield curve first, because that was the one that we were the most interested in. And we saw the formulation needed fixing, but then we can create angles that are in the range between 30 to 60 degrees. And it follows the theoretical angle of what we expect from the theory with the normal flow rule. The only problem that it would lead to more divergence in the model that would need to be tested in Panarctic simulations. And there's only one parameter, it's the tensile factor, because of the way this yield curve is constructed. Next, what we do is test the Mohr-Coulomb yield curve from IP, and I show here the intersection angle as a function of the slope parameter, so the angle that you saw of the Mohr-Coulomb slope. You see that we are in between what I called before the Roscoe angle theory and the Coulomb angle theory, but we don't have, first we don't create small angles, and then we have this high uncertainty on the angle, and we don't really understand what's happening. And it has a very slow numerical convergence, so something you want to avoid in high resolution CIS models. So we studied a bit more this yield curve, and we found out that the behavior of this yield curve is a bit more complicated. So we have, you can see in 1, we have full plastic state. In 2, we have states on the yield curve where we are half viscous, half plastic. It's also the case for the number 3. And 4, we are fully viscous. But then because of this, it's very complicated. So we decided to decide a new Mohr-Coulomb yield curve to try and to see if we can do better. So we got inspired by a paper by Hibler and Skolsten in 2000, where we use a Mohr-Coulomb yield curve with an elliptical plastic potential that defines the flow rule. So we're going to have a flow rule that varies continuously between divergence, going through shear, and then going to convergence. And so we have a plastic flow rule that's defined for every stress state on the yield curve. We can also use build on our work on the teardrop, so we can define a Mohr-Coulomb yield curve with a teardrop plastic potential, or a Mohr-Coulomb yield curve with a parabolic length plastic potential. Basically, with Jean-François, we tried a lot of different ways to define yield curve, and we found a lot of ways not to define yield curves. And then, for now, I'm only going to present the Mohr-Coulomb yield curve with an elliptical plastic potential. So, what we observe is that we can get small angles of small intersection angles in the range that are interesting to us. We still don't understand the clear relationship between the intersection angle and the parameters of the yield curve. You can see in black we have the Coulomb theory, and in blue we have the Roscoe theory. And what's actually interesting is that we are almost exactly in the middle between both of them, something we don't really understand. And that's what we are going to test now in the other Mohr-Coulomb yield curve that I was talking about before, with the teardrop and the parabolic lens plastic potential. So, yeah, so that's all. As a summary, I would say that, so we can say that with the teardrop and parabolic lens yield curve, we can reach smaller angles. We use a normal flow formulation, which is good because it's better for numerical convergence. For the Mohr-Coulomb yield curve, we have usually a non-normal flow rule formulations. We can create small angles, but we have this complex relationship between fracture angles and the yield curve. As a more broader follow-up ideas, we will need to see if actually using this new rheologies in a Parnacle setup will decrease the angles. Another thing is now we use deformation and the LKF and deformation data of the LKF to define a yield curve. Maybe we can use some machine learning, deep learning to try to see which yield curve we could define from just using the deformation data completely and not just like some metric with the angles. And there is, in the granular material modeling community, there is something called a mu-I rheology that use a Mohr-Coulomb yield curve that varies with the size of grain. So in our case, the size of the flows, that would be something interesting to explore. And maybe someday we can reach deformation in models that looks like this, with beautiful angles, small angles everywhere. And with this, thank you for your attention.
Okay, any question from the audience? Oui, François.
It's a very naive question, but when you see the satellite images, you can see big cracks and more narrow cracks. Is there a relationship between angles and the width of the cracks, or a relationship between angles and maybe the background thickness of the ice? Like, is there some preconditioning that would favor certain types of angles from the point of view of the state of the ice?
So, yes. Because what I do in my experiment is a completely flat surface of ice. It's 1 meter everywhere, 100% concentration. We know it's not the case. And the direction of the cracks will always be favored by some anisotropy that's embedded in the ice thickness. It's true. In the image, I mean, after in average, in some region, like the picture I saw, I don't know if this is there an influence here, but there is an influence.
He's asking if the thickness has an impact on diffraction.
Otherwise, in the rheology, there is nothing in it, like except the fact that there is thickness. There is no rheological term linked to the thickness.
Damien, can you comment on the fact that, like a few years ago, there was a paper by Wang where they observed the yield curve. I think it was the name of the title of the paper, observing the yield curve from satellite observations, and they came up with a kite. So, can you comment why you would get a different yield curve here?
Yeah, so you mean the one when they have a very like a bended line and then they use, that's a good question. We haven't tried this one. I don't like the fact that there's a cusp like this, like it will be the case with the Mohr-Coulomb, but in the one from Wang you have this little, this corner on the top, which is usually where you have a lot of stresses, stress states in simulations, which probably would be a problem, but it's something we could probably also explore. I'm not sure how they build their data set for the fracture, though I haven't looked really a lot at this paper, to be honest.
Okay, thanks.